Okay, so it's a good time to talk about autoencoder. So in the past, we mentioned autoencoder a few times, but we haven't formally or maybe took more details about this part. So yeah, so we remind ourselves that say we are using when we learn neural networks, right? Such as that in this case that we are given the input and output to be exactly the same, meaning that we are learning identity function given several input, right? So in this case that we have uh, the network like the 8 bits as the input and also 8 bits as the output, and we have always have the exactly same value from the input to the output, meaning that we are learning the identity function. Okay, the learning identity function may not be so interesting, looks like not so interesting, but actually our design is that in the middle we see that we don't have so many nodes compared to the input and output, right? So we are thinking about, in this case, some kind of input information may be compressed and saved in the internal nodes. In the later, the internal nodes information will be used to generate the output, which is equal to the input. Okay, so the simple example, simple design like this one usually is like we call the autoencoder, right? So given the autoencoder learning identity function, but with a relatively narrow uh, nodes, narrow layers in the middle, right? So maybe we can do some kind of compression, and maybe we can extract some useful information from the input. So this kind of approach usually will be used for compression and also for dimensionality reduction, right? If we do choose a few nodes compared to the input, okay? So this kind of information, this kind of structure will be quite useful later on in our deep learning models, right? So, and also here we want to emphasize that given the 8 inputs and 8 outputs, right? In the middle, we carefully choose 3 nodes. 3 nodes, the number of nodes will be 3 in the hidden layer, right? So given this, what we imagine that as the 3 nodes will be enough to summarize what we have from the input. And given that's one, right? The second is that starting from the 3 nodes, we can regenerate what we have seen from the input, which means that we can uh, recover the input information, okay, which is because we have input output to be the same, right? So if we check the hidden nodes, I think it's not that difficult to see that we for this here that we have the 3 numbers, right? 3 numbers mean 3 hidden nodes, okay? So that's the first column will be the first node, the second column will be second node, and third column will be third node, etc. Right? So you can see that we have for different kind of input, right? So the hidden values that we have will be, for instance, the first row we have 0.89, right? 0.04, 0.08. It's quite close to the value 100, okay? And if we focus on the second row, then what we have is quite close to 011, okay? And 010, 111, and 000, okay? And 001, and 101, and also 110. So after all that we have 8 different combinations, okay? In fact, that the 8 different combination, one for each different input or output, right? So that just because we know that 8 bits is equal to 2 to the power of 3, right? So we know that 3 nodes will be enough to summarize all the information from the input, which means that we can also use the same code to generate the output. So that's why the hidden layer representation is useful in this sense, right? So we can use the hidden information as the code for original data, and also the code can be used in decoding. Okay, so and also what we have here in the middle, right, the hidden layer is somehow summarize how much that we can represent. Okay, meaning the representation power, right? So more nodes, the meaning that we can represent more things, right? But of course, we have to make sure that the input will be enough associated with enough diversity, so that we do need to use so many nodes to summarize the input data. Okay, so the autoencoder in general, we have the original input data, right? And output data is like somehow the reconstruction of the input data. Okay, so in the middle will be the hidden layer. So from the input to the hidden layer, that's what we call the encoding. From the hidden layer to the output to the reconstruction, that means the decoding, right? So encoding and decoding will be used in different situations. Will be used in different situations. Okay, and but before now, we need to make sure that how to measure the input and output are the same. So maybe we can try something as easy as Euclidean distance. Okay, to find out the relation, the difference. But usually, that may not be the only choice, because sometimes for image analysis, right, making sure that the two images are identical pixel-wise may not be the only choice. You know that, right? So sometimes even we just shift the shift the image by 1 pixel, okay, to the left or to the right or to the top or to the bottom, right? So it doesn't change too much, but the error will be quite a lot, right? Okay, so maybe we need to make sure that in general, maybe we can find something other than the Euclidean distance. And using a narrow Z, yeah, so that's important when we want to do compression or noise removal or dimensionality reduction, okay? So how narrow depends on the application and depends on different data set. And of course, we can choose, we will have more than just one kind of structure, right? It doesn't need to be fully dense. We can try something like a convolutional design. Yep. And for the autoencoder will be used for different situations, just like I say, right? So let's say if we focus on the encoding part, right? Okay, so meaning that we just want to extract the useful information, meaning the feature, okay? Then the feature will be used for all the things afterwards, such as that if you want to try some kind of classification, for instance, logistic classification, logistic classifier, or some other classifier, right? So we can simply forget about the decoding part, right? So this decoding part may not be so important, right? So we just need the hidden node information, right? So you need to be clear that, okay, but at the beginning we still need to train all the things, right? Because we have to try the original network, right, to make sure that input and output are the same. So after that, the decoding part will be dropped, okay? Then the only thing like the hidden information will be used for the future prediction or maybe classification, right? Okay, so that's the situation that when we say feature discovery, right? We just need to find out what we have, what we can summarize from the input data. Okay, so yeah, so a lot of design that we can think of, right? So we can use, let's say, the new feature, right? In the new training set, right? Just like in this case, right? Just like in this case. in this case, okay? And at the same time, we can also try to concatenate both the feature and the original data together, right? Like we can put, for instance, some kind of design could be like the following, right? Maybe we can try to see, let's say, 8 different nodes, right? For instance, right? Okay. Okay. Then suppose we summarize to be 3 nodes, right? The 3 nodes will be used. Okay. And also possibly we can also allow things to go to, let's say, go to the we allow shortcut from the n-1 layer to n+1 layer, like that. Okay, so maybe we can allow this to, which means that we're going to have the input, both of the input and feature included together. Okay, yep. So that's the autoencoder for the feature discovery, right? Just like we say, decoding is not important in this case. On the other hand, we can also talk about, let's say, if we try some more complicated situation, like if we have the input images, right? So we want to reconstruct the original input images, right? So by doing that, we can find out what could be the hidden code in the middle, right? And now this case is that for the image analysis, maybe one of the interesting application is that we don't just focus on the encoding, right? Instead of that, we focus on the decoding, right? Which means that maybe we want to find out what kind of code that we have, and we can use the code to generate new images like a coffee cup, right? Okay. Of course, there'll be some results, some research working on this part, right? So basically, what we have here is that maybe we can try some kind of randomly generated vector as the input as the code, or some kind of a subset of the code space, right? Then we will use that to generate meaningful images like a coffee, like some kind, like the original data, right? Okay, so just like we emphasize, we don't have to using the MSE to measure the area, okay, between the input and output. And we are going to try to decide what kind of code that we can use to generate meaningful data, right? Okay, so that's for the case that when we focus on the decoding part. Okay, so next we talk about generative modeling. So let's take a break.